Hello Algebra 2, welcome back. In this video I just wanted to go over mostly a review of what we were just covering before we went to break, just as a refresher for you, and then after this the next ones will be extending that to new stuff. So hopefully this will help you kind of get back into the swing of things. What I wanted to start with, though, is something that I don't know how much I've spoken about this before. This is just to help you keep things straight in your head. There's a little bit of ambiguity in the way that we write things in algebra, and I just wanted to make sure that you guys are at least aware at this point okay. I hope I'm on the right audio capture device. I at least want you guys to be aware at this point that there are these differences in the way we use certain symbols in different contexts, and then hopefully as we work through this you won't be as confused, or at least hopefully that confusion will clear up as we get more practice. But I'd just like to explicitly explain a few different ways that we use the same symbol that could be confusing. So to start with, if you look on the right of this screen, you'll see the top two statements that I've written. They look very similar. X plus x equals 2x, and 2x equals x squared. Those are actually two different types of statements. The first one is called an identity, while the second one is called an equation. The first one is not an equation, even though it has an equal sign. So I think we even had an assignment where it said, what's an equation versus what's an expression, and the equation was basically saying, well, it's like an expression with an equal sign. Well, I guess we need to be a little bit careful, because you can have an expression on one side and an expression on the other with an equal sign separating them. We'll call one the left-hand side and the other the right-hand side. The shorthand for that is LHS for left-hand side and RHS for right-hand side, where it's still not an equation, even though it has an equal sign. So that's something I'd like for you to be aware of at this point, because that might be confusing. The top statement is what we would call an identity. And the reason for that is that if you plugged in numbers for x for the left-hand side versus the right-hand side, let's say you plugged in 2. All right, well, x plus x, that would be 2 plus 2. That should be 4. What about the right-hand side? 2 times x, that'd be 2 times 2, that's 4. So they're the same. That's good. What if we plugged in 3? 3 plus 3 makes 6. 2 times 3 makes 6. Still the same. How about 100? 100 plus 100 makes 200. 2 times 100 makes 200. Still the same. There's actually nothing you can do there's no value you can plug in for x, whereas the left-hand side would not be the same as the right-hand side. There's no way to make them different, the two sides, with any value of x you choose to plug in. Therefore, this is called an identity, because they're the same. The two sides of the equal sign are the same always, so for any value of x. So we would call those an identity. And if I graph them, try to ignore some of the stuff I have on this graph here, but I'm just going to do the x plus x and the 2x for the identity, and you'll see that when I turn on the x plus x, I get this line, and when I turn on the 2x, I get the same line. There's no value of x where they're different. There's no place where the left-hand side and the right-hand side give different outputs for any given input. So that's an identity. Okay. So they're the same. The next statement we would call an equation, because let's say I plugged in 5 for x. Well, 2 times 5 would be 10, whereas 5 times 5, 5 squared, is 25. So if I plugged in 5, it would make the statement read 10 equals 25. That evaluates as false. That's not true. So if I plug in 5, I get false. So this thing does not work. It does not create a true statement when I plug in 5. If I plug in 10, I get 20 equals 100, which is also false. It doesn't make a true statement. If I plug in 0, I get 0, 2 times 0 is 0, equals 0 squared, which is also 0. 0 equals 0. That's actually true. So there are special values of x that I can insert into the second equation, or the second statement, which make it true, whereas there are other values of x, other inputs, whereas the left-hand side would not equal the right-hand side, and it would make the statement false. So there's only select inputs for this statement that would make a true statement once you plug it in. And there's plenty of others, most others, where you plug them in and it makes a false statement. That's why this is called an equation. It's not always true. It's only sometimes true. It could never be true. It could not be true at all. There could be no input that makes it true. But the process of finding the inputs which make it true, which make the left-hand side equal the right-hand side, is called solving the equation. And the x values that make it true are called the solutions to the equation. So this one's different than the identity because every value of x makes the same on both sides, whereas this one, there's only special solutions that make this thing true. So if I have 2x, which is my left-hand side plotted, and then I plot x squared, I see that they're different shapes. And if I zoom in, it turns out where they cross, which is at 0 and at 2 for the inputs of x. 0 gives me 0. They both give me 0. And whereas I plug in 2, I'll get 2 times 2 is 4, and 2 squared is 4. So those are my 2 and only 2 solutions on the real number line. Only those 2 real numbers will give me the same result, and you can see that on the graph as an intersection. So these are the only 2 solutions. So those are what I'd be looking for if I were trying to solve this equation. I'd be looking for those solutions, those values of x which make the plot of the left-hand expression and the plot of the right-hand expression intersect. They coincide. So that's one thing to be careful of. So here we're using the equal sign to make an identity. Here we're using the equal sign to make an equation. What we often do in Algebra 2 is we're using the equal sign to define something. So it's a little different still. So we've seen that y equals x squared. What we mean by that is, okay, take 2, plug that in for x, 2 squared makes 4. So if I go on the x line, parallel to the horizontal axis 2, the output, aka going parallel to the y-axis, I should go up to 4. Y equals the x value times itself. So 2 times 2 makes 4. So at 2 for the x value, I have 4 for the y value. So that makes some sense. We've also dealt with this notation, function notation, where we write, it's pretty much equivalent, f of x is equal to x squared. Remember, a function we mean by if something is a function of something else, we mean that it varies with that other thing, that it's dependent on that other thing. So for instance, the length of my shadow is a function of my height, or the amount of weight I gain is a function of my daily calorie intake versus how many calories I burn per day. If something depends on something else, it's a function of that thing. And we write that with parentheses. The parentheses don't in this case mean multiplication. We call it like a hungry operator. The function eats the x, and then it will leave in its place the output value. So it's a little different the way we write it. So I just wanted to remind you of that. Now this here is sort of like, okay, y is some function of x, but it's kind of like when we write that like like y equals a, where a is an unknown number. Okay, it's a number, but we're not telling you what it is, so it's a little information is hidden. Well, when we write y equals f of x like this, we're telling you that y itself is a function of x. So I could equally just say, y is a function of x, and write it like that. But when I write it like this, it means that y varies with x. Y depends on x. Now, f of x could be x squared, f of x could be x cubed, f of x could be the square root of x. Again, we're hiding information from you. You just know that y varies with x, that y depends on x. I'm not telling you the specific relationship. Just like with y equals a, where y is an unknown number, in this case, y is an unknown function, an unknown expression on the other side. Now if f of x equaled x squared, and you said y equals f of x, that would mean that y equals x squared. So it's kind of that transient property where if a equals b, b equals c, then that means a equals c. We could write it that way. But when we're trying to express things in a generic way, so it doesn't matter what the function is, you can do things to any function and it will work the same for any function. We don't write every possible example function for you, even though I'm going to go through some examples with you today. We write it like the last example here, y equals f of x, where this represents some generic unknown function. So I'd like to show you kind of how that works. So here's, I'm using as the parent function f of x equals x squared here. So if that's the parent function, then, well, let's say it doesn't have to be. It could be x cubed. It could be square root of x. It doesn't matter. But I'm just trying to show you doing something to the generic version, what it would look like on the explicit version. So if I write it, or specific, I should say. So if I put the minus sign outside of the function, where the function is x squared, it would look like this. Whereas if I put the minus sign on the variable, on the argument of the function, it would go, I'd put parentheses around any x I see, and I would put the minus with that x. So that's how, or if this was a square root, if that square root of x was my parent function, I would put it in the square root with my x for this one. The idea is that this works for any function. I'm just writing it in a generic way, but you can apply this to any function. Likewise, let's say I add or subtract some number, a is some unknown number, to my variable. Let's say I'm subtracting 2. If I put it in with my x, that would move my graph to the right 2 units. Every point would move to the right 2 units. Whereas if I put it outside of the function, not in with the x, then every point on my graph would move down 2 units. So one's a horizontal, we call it a translation, and that's a shift. Whereas this other one is a vertical translation. But when we write it in this generic way, we're just saying do it either to all the little x's that you see, or just hang it outside to the far right, have it be separate. Don't put it in with the x, have it its own term. Don't put it inside of individual terms that are already there. Make a new term hanging off the end. That would make it a vertical translation, whereas before it would make it a horizontal. This is the generic way of writing a vertical stretch or compression, depending on if a is bigger than 1 or less than 1. So if I put the a here, let's say it's 2, so I'm multiplying outside of the function on the whole function, then it's a vertical compression. Oh, I'm sorry, stretch in this case. Whereas if I put the multiplier, the constant that multiplies, on the argument, on the x, so I put a parentheses around the x and I put the 2 in there with it, that would make a horizontal compression. So if I put it with the argument, it's horizontal. If I keep it off of, outside of the function, it's vertical. Same here. If it's outside of the function, it's vertical. If it's in with the argument, it's horizontal. Again here, if I do a negative outside of the function, it'll be a vertical reflection, where if I put it in with the argument, it'll be a horizontal reflection. So that's just a refresher. But this is how we use function notation to represent in a generic way, in a general way, what you could do to any function, and it would have the same effect. So I'd like to show you some of that. And so I've got different functions here. I'll turn some of them on. So here is y equals x squared. Again, if I put it outside of this function, I can make it go up or more, depending on what I add. I can make it go down more, depending on what I subtract. Whereas if I put it in with the function, I got to make little parentheses for that. If I do -1, I go to the right, -2, oops, -2, what have I done? There we go. So if I have minus nothing, it's right where it should be, but -1 goes to the right, -2 goes to the right. If I add 1, it goes to the left, add 2, it goes further to the left. So that's just how that works, and we've had some practice with x squared. So yeah. Now, the idea though is the reason why we write it in this generic way is because let's say the function is something that we haven't dealt with before. Let's say it's sine of x. So we'll eventually work a little bit with sine of x. So that's coming up this semester. But it looks a little different. But likewise, if I go in with the x and I say -1, just like before, it's going to move every point to the right 1, or -2, or -3. It keeps moving to the right. Whereas if I said +1, +2, +3, it's moving to the left. Likewise, if I put a minus on the x, I will have a horizontal reflection, so you'll see it flip that way. See? And now this is going to look kind of similar, but if I do a minus outside, it should be a vertical flip. And I know those look the same, but one really is a vertical and one really is a horizontal. Just to show that, if I put a 2 outside of the sine function, I will have a vertical stretch. So you'll see I get a stretch. If I do 3, it stretches more. If I do a 4, it stretches more. Whereas if I put it in with the argument, it'll be a horizontal compression. So it'll get squished like an accordion. So here it's squished, squished more, squished more, squished more, squished a lot. But it's horizontal when it's in there, and it's vertical when it's out here. And you can kind of see that based on if you're outside the function or if you're in with the argument. If you're in with the x variable, it does 2 different things. And just to show you that even though putting the minus here looks the same as if I put the minus here, one really is a horizontal reflection, one really is a vertical reflection, even though those look the same. And you can tell because if I put a 1 outside, it does nothing. But if I put a 0.9, it shrinks a little, a 0.8, 0.7, 0.6, 0.5, 0.4, it's squishing vertically. Let's say if I go 0.1, 0.01, now if I go to negative, so if I go past 0, 0 makes a flat line, but if I go to negative 0.1, you see that the hump that was higher on the right, here it is again, it looks like this. But if I do 0.1, it's smaller, and if I do negative 0.1, it really is a flip vertically. Negative 0.2, negative 0.3, negative 0.4, negative 0.5, and if I go to negative 1, it will flip vertically. A reflection is really just a vertical stretch that went, a vertical compression that went past the 0 mark and then went where it actually flipped the sign of the values. Whereas putting the minus here really is a horizontal reflection because I can put a 0.9 or a 0.8 or a 0.7, 0.7, 0.6. So I'm getting smaller. 0.2, 0.1, 0 makes it flat. I'll do 0.1 again. A negative 0.1 actually, well, I guess it isn't as convincing as I thought it'd be, but it kind of stretches out flat and then it kind of comes back the other way, so it's kind of weird. And then you got minus 2, minus 3, minus 4, and now it's coming back and it's squishing in, and once you get to minus 1, it's actually looks like you just sort of horizontally flipped it. So even though you haven't dealt with this function before, using this generic way of expressing functions kind of tells you that what you did with x squared works for any function, even sine of x. Lastly, I'd like to show you a more complicated function. You can see that this has many terms. It has 4 terms. It has a constant term. Oh, shoot. It has a linear term. It has a quadratic or a squared term, and it has a cubic term. If I plot it, it looks like a cubic, because it is. I'll show you how that works. So if I wanted to flip this vertically, I could go into, I could parentheses around the whole thing, and I could put a minus out front, and I have flipped it vertically. I'll show you that. So that is a vertical reflection. That's the same, I mean, you can distribute that minus throughout the parentheses, so it's the same as flipping the sign of every term. So that would do that. But if I put parentheses around every x, so it's not just one thing, because this has multiple terms with x's in it. So those are my x terms. If I went in, I'm going to copy all that, paste it here. So they're the same, but if I put a minus on every single x value that I have, what I get is a horizontal flip. So instead of having the higher thing here and then the little dip at the right and it goes up, if I do it with the minus on all the x's, it has the higher thing on the right, comes down, dips on the left, and then goes up to the left. So this did a horizontal reflection. So it's a little more complicated when you have multiple terms, but it's the same if you put the minus sign outside on its own. It will do a vertical reflection, whereas if you put it with the argument x, and with the generic, it's not telling you that there's just one x. There could be lots of x's in this expression, but you have to do it to every single x. Everywhere you see an x, you have to do it, and then you can achieve a horizontal reflection. Hopefully that's not too confusing. It's a little bit of work, but hopefully that is conceptually something that you can follow. So yeah, that is how that works. What else did I want to go over? I guess I'll talk about translations. So I'm going to take that one away. So let's say I add a number out front. So I've got the 12. Let's say I want to add 5. Plus 5. I've just moved everything up. So I did it outside of the function. I added another term. I said plus 5. I could have just made this a plus 17 instead of a plus 12, but because you can combine like terms in your expression. But adding the 5 just moves everything up, just like it did with x squared. If it's outside on its own, it moves it up. Whereas if I put it in with every x, so if I put the plus 5 here, plus 5 here, and plus 5 here, all I've done is I've moved the function to the left 5 units. I had to do it to every x, not just one of them. But if I do it with the x's, just like this generic function explains, it will move left if I add, and it will move right if I subtract. So that's just something I want to explain. I want to explain function notation. I want to re-explain what we call the transformations of a function. We have reflections. We have translations, the shifting up and down, left and right. We have the compression and the stretching. There are others that are a little bit more complicated. There's rotation. And we will see inverting the coordinates. That's basically where you just take your graph and you kind of flip it and then rotate it 90 degrees. That's kind of that's another one we'll get to eventually, probably next week. But I just wanted to give you a refresher on what the transformations are and how they work, and let you see them on Desmos. I'm going to put up assignments for you to work through. You can try to do those on your own. I will be available during our class time, I think for the 1A section, that's from 8 to 9. And for the 2B section, that's, I guess, 9:30 to 10:30. I'm going to be here and here to take questions and help you through your assignments. They're practices, but you'll get points for them. And if you need any help on them, I'm here. Just a reminder to work through, when you're working through the assignments, you have multiple attempts. Try them, and if you can't figure them out after a couple of attempts and you're not sure what you did wrong, reach out to me so that I can help you before you take your last attempts. Anyway, I hope that's reasonable for you for today, and I will get more of these posted within the next day or two. Welcome back. Happy New Year. Hope you had a good break, and I hope you have a great rest of the semester.